So the first exercise of today is to prove Young inequality. That's written right here. And yeah, so try to prove it. All right, so the key point to prove the Young inequality is to remark that the logarithm function is concave, meaning that, so sorry. So if I draw here, the log function is like that. So if you take 2 points here, and so you look at a point which is between these two, let's say that. So here you have theta alpha plus 1 minus theta beta. So with theta belonging to 0, 1. Since the logarithm is so there's people waiting here. So since it's concave, it's the function is above the line here. So you can say that the logarithm of theta alpha plus 1 minus theta beta is greater than theta, the logarithm of alpha, plus 1 minus theta, logarithm of beta, which, so you are comparing 2 points here. This is here, and this is here. Okay, this is here, and this is here. All right, so we are going to apply this, the fact that the function is concave to a to the p divided by p plus b to the q divided by q. And I claim that this is greater than 1 divided by p log of ap plus 1 divided by q log of bq. So why can I do that? Why can I do that? Because 1 divided by p plus 1 divided by q equals 1. So you can say my 1 divided by p is my theta. All right. So once I have that, I can remark that this is, so the p here can come, I can take it out, so it becomes ln of a plus ln of b, and this is ln of ab. So now if I apply the exponential function, I got the results. So I got the result. is greater than AB by applying the exponential function here. So sorry, here and here. So next we consider the Holder inequality. So try to prove it. All right, so now we are going to prove the Holder inequality. So to do that, we are going to apply the Young inequality from exercise 6, but not to F and G, but instead to F divided by the norm of F in LP and to G divided by norm on G in LQ. So we apply Young inequality to. So what do I obtain? If I do that, I obtain that F divided by F divided by its norm times G divided by its norm is less than 1 over P times F, and I take that. So the single bar is the absolute value, but the double bar is the norm in LP and LQ. So I have that. And divided by Q. So if I take the integral of that, I obtain that the integral of F G divided by norm of F in LP, norm of J in LQ is less that, and now I take the integral. Of course, this is a plus here, not times. So this is less than, now I take the integral 1 divided by P integral of F to the P divided by the norm in LP to the P plus 1 divided by Q integral of absolute value of J of G to the Q divided by the norm of G in LQ to the Q. But this is 1 now. This is 1 because I can take out the norm. The norm is a number. So so I can take this out. So I obtain, and this is also 1. So this is less than 1 divided by P plus 1 divided by Q, which is 1. So it's done. Because now I have that integral of F G is less than norm of F P norm G Q. So next we move on with exercise 8, which is about Minkowski inequality. And so it's the key tool to prove that the formula with the integral is a norm in LP. And so Minkowski inequality deals with the property of subadditivity for this norm. So next, we want to prove so that the norm of f plus g in LP is less than the norm of f in LP plus the norm of g in LP. So let's do that. So first, for all x in my domain, I can always write that this is less than all right. Now what I am going to do is apply the Holder inequality to those two terms here and here. Okay. So let's start with this one. So f, so I forgot now the x. So f times f plus g so this is less than the norm of f in LP times the integral of f plus g p minus 1 times q to the 1 divided by q. This is by Holder inequality. All right, but I can do something about that because so you have 1 divided by p plus 1 divided by q equals 1. So this implies that q plus p divided by pq equals 1, which implies that q plus p equals p times q. So which means that here, this term here, p minus 1 times q equals pq minus q equals q plus p, thanks to that, minus q equals p. So this is nothing, this is p. All right. And so this whole integral, I can write it. This whole thing, I can write it as the norm of f plus g p divided by q in p. Do you agree with that? So I will write that. So what I obtained is that the integral of f times f plus g p minus 1 is less than f p times f plus g p divided by q. All right, I can do the same with g. And if I sum up the two, so let's call this A, let's call this B, I obtain that A plus B equals F P plus G P times F plus G P divided by Q. Yeah. And so I started with what? I started with this thing here. So what I obtain here so if I sum up, if I summarize what I have finally is that the integral of f plus g to the p, this is a plus b. I mean, this is less than a plus b, so I got that, and this is the same. So now I am going to divide this quantity by this one. So I obtain the integral of f plus g p divided by norm of f plus g p divided by q. So this is exactly norm of f plus g p divided by f plus g p divided by q. So this is norm of f plus g p minus p divided by q. So let's do this computation. P minus p divided by q is pq minus p divided by q. And this is p plus q minus p divided by q. And this is 1. And I forgot to just, this is a p, right? This is the norm in p. There's p always. So that's done, because this is exactly f plus g p. So we are now giving a little bit more of details about the LP spaces. So this section is inspired by the book of Bresis and the book of Regin. It's a mix of those. So there's some material on Bresis about basically the Lebesgue integral, and I use that because it's short and it's sufficient for our purpose. So to define the LP spaces, you need to remind what's a measure space. So you have omega, for example, r to the n or other, and you define a sigma algebra on omega and a measure, a positive measure for our purpose. So a sigma algebra is what? Is a collection of subsets of your omega such that empty set belongs to. So the empty set belongs to the sigma algebra. It is stable by the complementary, and it is stable by countable union, right? So there's some authors construct this thing by analogy with with topologies, which has a similar type of definition. Okay, once you have your omega and your m, you define a positive measure, which is an application from your sigma algebra into positive numbers plus infinity, because for example, R endowed with the Lebesgue measure as infinite value. So you need to include the plus infinity. And so the measure of the empty set is 0. And when you have disjoint sets and countable family, you have the mu of the union is the sum, right? And so in this context, the subsets that are in M are called the measurable sets. We should also assume that sigma is, so omega is sigma finite, meaning that you can write omega as a union of some subsets, and each subset has a finite measure. Okay, next. Yeah, so you have sets with the property that mu of E equals 0, so we call it the null sets, and we say that a property holds almost everywhere if it holds everywhere on omega except on a null set. And so when you have that, you can define the integral of f. And for example, I refer to the book of Regin, but there's many others for the detailed construction of the integral. A fundamental example, though, is when you take omega is r to the n, which is very classical, and it is the more often used in this course. And then on Rn, you have the natural measure, which comes from the measure of cubes. The natural volume, you generalize that, and you arrange to have some measurable sets that satisfy the conditions of a sigma algebra, and you obtain the Lebesgue measure, and that's how we define the LP on this course. Okay, once you have that, you have some theorems that will be useful to prove that LP is is a Banach space, that LP is complete. So we will need the monotone convergence theorem. Is there a question? No. Assume that you have Fn, so they are measurable functions. And so I didn't say what's measurable functions. I refer to origin. It's very well written, this chapter. You can have a look at it. And actually, you know it from the previous years of your math courses. So, and next, you assume that the sequence of function is increasing. Okay, so meaning that you have that for almost all x in omega. And that, so AE stands for almost everywhere. And furthermore, you assume that Fn of x converges to f of x. Then f is measurable, so you can, and you have that the integral of Fn converges to the integral of f. All right. This is a theorem that we will use in the proof. Okay, next. The Fatou's lemma. It means that when a sequence Fn, when you can take the integral of Fn, the limit infimum of Fn, you take the integral of that, is less than the integral of the limit inf. Okay, so with that in mind, I suggest that you think about, you start to write how to prove that LP is a Banach space. Sorry. Okay. So I don't know what's that. Okay, so try to prove that LP is a Banach space. Yeah, so there was a problem in the document, in the Fatou's lemma. So thanks to the remark of the students, I corrected it. So the Fatou's lemma, of course, writes like that. So now try to prove that LP is a Banach space. Yeah, try to do that.